Okay. Well, thank you. It's very nice to be here. I think this is the first time I've spoken I've spoken here several times, but never at a teachers conference. So, yeah, welcome. Okay, so I will talk about, well, in some sense, I'm going to talk about everything, but I'm going to do it in a very superficial way, and then the other speakers will go into a lot more detail. But I'll try to give you like an overview, I think, and it's intended to be pretty accessible. You don't have to know very much quantum field theory or anything like that. And that will hopefully give you some framework to follow the rest of the talks. But okay, so I entitled this, and then there was mass from the Higgs boson to the unknown. This is the CMS experiment, part of the CMS experiment actually, which is 100 meters underground at a place called Cessy in France. If you go above ground, there's just cows, and you go underground, it's like a James Bond, underground empire. There's the other experiment is Atlas, also roughly 100 meters underground. And this was a new piece of the experiment that we just put in recently. This is an end cap that helps detect muons that are coming out of the interactions. Okay, so I wanted to give you a very basic overview. We use high energies to probe to smaller and smaller distance scales. Higher energies are smaller frequencies. They probe smaller things. This is part of what, in one way, you can interpret what particle physics has done over the last century. It's just probed smaller and smaller scales, higher and higher energies. We know what a hand is, and that scale is easy for us to understand. An atom is a few billionths of an inch. Inside an atom, you have a nucleus with protons that are about 1/10,000th the size, 1/10,000th the size of the atom. We know that inside the proton there are quarks that are another factor of 100 or so smaller. So right now the LHC is actually probing down to about 10 to the minus 20 meters. This is 10 zeptometers. I didn't know this unit until one time I was giving the talk and somebody came up afterwards and told me. So that's kind of what that scale to an atom is what an atom is to a human. So that's how far down in distance scale we are. It's kind of unfathomable. And you can think of it as kind of nanoscience. Now, the term standard model has come up a couple times. Really, over a century or so, the discovery of many subatomic particles and many breakthroughs in theoretical physics has led to the creation of what's called the standard model of physics, which is like a new periodic table of the fundamental elements, if you like. And the particle nature of the standard model is shown here. There are you see these three columns, three generations, if you like, of quarks and leptons. And then there are also force carriers. And in the middle of it all is the Higgs. So in some sense, it's very, very simple. We spend a lot of money, and this is all we've learned. But it's good, because it should be small. We want it to be simple. That's the goal. And it's described by one simple equation. So these are fermions here on the left. This is Enrico Fermi. This formula is wrong, and it tells you, whenever you have a photo op, check the board. I'm sure he didn't make it. I'm sure he didn't do it. And then there are bosons that they're named after Satyendra Nath Bose, who wrote a letter to Einstein explaining how bosons should behave statistically. Einstein realized it was a good point, even though this guy's from India and not even a PhD physicist. I don't think I would have even read the letter, because we can, who is this crazy? But he was right. Okay, there's another look at the standard model looking on a log scale of the masses. I don't put the neutrino masses in yet because we don't know what they are, but they're tiny. We know they're non-zero. That's a big discovery. And then you see there's the three generations keep going up in mass by lots, big factors, right? And the heaviest known particle is the top quark. These actually are all we think we need, okay? If everything you see around you basically is made up of those. But the rest are what is really, even though we don't see them in everyday life, it turns out they're very important to how the universe works. And that's, to some extent, why we do particle physics. We're not just looking for particles for the heck of it. We're, in some sense, looking for, if you like, the genetic code of the universe. We're trying to understand how does the universe work. These particles are all interconnected in some way or another. And so to understand how everything works, we have to know the basic content of the elementary particles. The last piece of the puzzle was the Higgs for the standard model. And we don't know why the masses are so different. This is something the standard model doesn't tell us. We have to put those in by hand. So the Higgs, the Higgs field is something that came into existence early in the universe. If you like, all the particles in some sense were massless, moving at the speed of light. When the Higgs field came into existence, it froze out everywhere, and some particles began to interact with it, if you like, making it impossible for them to move at the speed of light. And the more they interacted, the more that was true in some sense. And so that's how they acquire mass, because a particle moving at the speed of light has to be massless. One with mass can't move at the speed of light. So this is just kind of a schematic of a massive particle interacting with the Higgs field. And that was speculated to be there. It was the only way, the simplest way to make everything work. But there are many problems associated with this type of particle that was being proposed. So it wasn't guaranteed to be there. Okay, so that happened about a picosecond after the Big Bang, a thousandth of a nanosecond. So we have to, if you like, recreate what the universe was like, the conditions of the universe 1/trillionth of a second after its beginning, if we're going to study what happened and what this Higgs is about. That's when the universe was 45 million billion degrees. And to get that high of an energy, we were accelerating up until recently protons with roughly 4 trillion electron volts. And now we've gone up to 6.5 trillion, in fact. And we collide them head on. And to do that, to get to that very high energy, we use the Large Hadron Collider. This is the valley between the Jura and the Alps, the Jura Mountains and the Alps. This is Mont Blanc over here. And this is the CERN accelerator complex. We start with a small accelerator, accelerating the protons, inject them into a bigger one where we can accelerate them more, inject them finally into the yellow one there, which is the Large Hadron Collider. And you see it's a very big machine. I've been told it's the biggest machine ever built, but I don't know how you actually measure these things. Somebody also pointed out that if you think about astrophysics experiments using multiple satellites, they're bigger because they're separated by a huge amount. But I think that's cheating. So the design goals were to cover all the possible masses for the Higgs that we thought could happen, which were roughly 100 to 1,000 times the proton mass. And then to search for new particles that are up to many thousands of times the proton mass. And you'll hear about that more from others. This is the timeline. The very first study started in 1984, 10 years to get approval. Construction started roughly 10 more years from approval to starting installation. And then from the beginning, basically, to the very first collisions was a quarter of a century. So it takes us a long time to do this stuff. In fact, when it was first approved, we didn't have the technology we needed. We had to still work on inventing it. And it required a lot of new concepts and innovations, magnets, cryogenics, electronics. It was a huge worldwide effort, probably 60 countries overall. And then, of course, patience, perseverance, optimism, trying not to go insane, waiting for it to finally happen. It just seemed like for so long it was never going to happen. I just remember that. It just took so long. This is down in the tunnel. So you have a 17-mile circular tunnel, 300 feet underground, that's filled with lots of instruments. These are the dipoles. Dipole magnets keep the particles on a circular track. And I like this slide. It's courtesy of Jörg Benninger. I changed the title. I say it's like Swiss chocolate, so you're going to have to figure out what the heck I'm talking about. So the magnets store about 11 gigajoules of energy, okay? And that's enough energy actually to melt 12 tons of copper, just the magnets themselves. It's actually the kinetic energy of an Airbus A380 at 700 kilometers per hour. And how much energy is actually stored in these little beams? That's about 350 megajoules. And that's equal to about 23 kilograms of TNT or 15 kilograms of chocolate. So you didn't know that chocolate had more calories than TNT, I bet. I don't know. So the pressure inside this thing, inside the vacuum, that's the vacuum pressure in the beamline is actually lower than the pressure on the moon. It's some of the best vacuums ever produced. And the magnets are cooled with 100 metric tons of superfluid helium. So this is colder than outer space, actually. And it's the largest cryogenic system in the world. So let me tell you quickly about the experiments. There's another picture of showing where the accelerator is, and you get another chance to sense how big it is. This is the Geneva airport, which can land Airbus 380s, in fact. So it's a big thing. And you can see the little ring, then the bigger ring, then the LHC. There are actually 4 main experiments, but the 2 big ones are CMS and Atlas. And you have people here from each of those, me and Tom. There are a couple of other experiments that are very dedicated to specific types of physics, and I won't talk about those. I don't have time. So again, we collide protons at the center of each of these experiments over and over and over. It's not just like one shot. We're doing it, we run like a casino. We try to stay open all the time. And we just run and run and run, and we have 40 million, roughly 35 million or so beam crossings every second inside of each of these experiments. And we try to do that for 10 to the 7 seconds per year, roughly speaking. Atlas. This is a cartoon of the Atlas detector. It's really big. It's 7,000 metric tons, about 1 Eiffel Tower in weight. Okay. The length is about, well, it's more than half a football field, more than 6 stories or so. It's really quite big. In fact, those are people there. I think they're littler people. They're cheating a little bit, but they're real people. Maybe they're French. I don't know. You have 2,000 miles of cables, something like that. And the size and the mass is what's really dictated by what you need to measure momentum and energy of these very high energy particles. For instance, a particle coming out at very high energy, if you think about it, we'd like to measure its momentum. How do you measure its momentum? You apply a magnetic field and it will start to curve, right? And the curvature will be related to its momentum. If they're extremely high energy, how do you do that? You either have to have a really strong magnet or a big lever arm. You have to be looking over a very long distance. So in some sense, Atlas is really huge to look for particles that are very high energy. And CMS has a slightly different approach, but this shows the Atlas cavern, and it was empty, obviously, to begin with. This is in 2003, and this shows the installation of the toroidal magnet system that is really determining this scale of this experiment. So here's a picture. That's a real person. And there. So Atlas has something like 38 countries, 177 institutions, 3,000 scientific authors. About 1,800 have a PhD, and 1,000 or so are hoping to have one. And inside, what's amazing, I mean, this is before the rest of the detector was installed. Now that's a very packed space. Tom will probably show you some pictures, I think. There's amazing technology that was developed in filling every square inch of this, a cubic inch of this volume. CMS, this is the experiment I was on. I am on, actually. We had a cavern that was late in being prepared for us, partly because it was under the glacial moraine where the land is coming up to the Jura Mountains. Water is constantly flowing there, so the land is really wet. For 40 meters down, it's just mush. And when they tried to excavate the shaft, they kept caving in, so they had to actually freeze the ground with liquid nitrogen and excavate it while it was frozen, meter by meter, and build the shaft. So we were late getting and we knew we would be late getting our cavern, so we had to build the detector on the surface and lower it in 13 or 14 pieces, 25 stories. And these are several million pound objects. And the clearance we had coming down was about an inch. So it was quite a feat. We had to rent the largest crane in Europe. This is the heaviest piece. It's 4.5 million pounds. And that's the superconducting magnet we have at the center of our experiment. It's the largest, most powerful superconducting magnet. I wanted to point out that we're good citizens. We recycle. These are empty shell casings from the Russian Northern Fleet, World War II. They got melted down. Here's a cheerful guy. And we turned them into our hadron calorimeter. Partly that's because NATO bombed the first factory we were going to use in Serbia. They did. This is the last piece going in. It's not so important what it is. What I like to show you this for is to give you, again, a sense of scale of these experiments. So these guys see where they're standing, and this piece is quite big, right, that they're putting in. But if you step back, that's those guys. So you see the rest of the experiment. And then this experiment, CMS, is quite small compared to Atlas. Okay? So they're quite enormous and extremely sophisticated, and you can see why it took 25 years, I think. This is, again, the CMS collaboration. Like Atlas, there's a lot of countries, about 42 countries, 190 institutions, 2,200 scientific authors, 1,400 with a PhD and 800 hoping to get one. And the total weight is 2 Eiffel Towers. It's heavier than Atlas by a factor of 2, but it's smaller. It's only 4 stories instead of 6. It's only 100 feet instead of about 175 or whatever you guys are. And the reason for that is that we use a very, very powerful magnet. So we don't need to be as big, so to speak, or we can be compact because the magnetic field is strong and it'll make the particles curve a little bit more. Okay. And inside is, again, lots of fancy electronics filling every cubic inch. We use semiconductors for tracking. These are lead tungstate crystals to stop photons and electrons. They look like glass, but if you try to lift them up, they're heavier than lead, quite heavy. And Newsweek called it the biggest experiment ever. I like to show this because, and then it says in parentheses, and it's European. First of all, this is CMS, which is smaller than Atlas, so this is not the biggest biggest experiment ever. The other thing is, everything you see here was built at the University of California. But what can I say? I mean, Newsweek went out of business. There must have been a reason. I heard they're back, though. I don't know. So here's a picture of the CMS again. Before we put, this is the central detector, and you can see these kind of concentric cylinders, right? Structure. So that's for particles going straight out from the beamline. You're looking, if you're looking down the center, you're seeing what the beamline sees. It goes right into the center of that bullseye. There's another one coming from the other side. They collide. Things come out sideways and go into these cylinders, and we look at what's happening on the different layers, okay? And I'll show you a little schematic of that. But I wanted to point all that out because then we cover this with caps, many layers of end caps, so the things coming out in the forward directions, you know, kind of more parallel to the beamline will also be detected. But this gives you some idea how it works. There's a little schematic. I got rid of the real detector. So we have many layers, as I said. The first large volume, kind of going out to the black ring almost, is our tracking region. And there we try to make a detector that can pick up the traces of the particles making their curved orbits if they're charged, right? And we want that to be extremely lightweight, as ethereal as possible, because we don't want to disrupt those paths, right? So we build detectors. In this experiment for CMS, for example, we have something that's kind of the size of a semi-trailer that has about 100 million channels of electronics, and it weighs 1,000 pounds, which is really little, you know. Then, outside of that, once we know their trajectories very nicely, and we know the momentum, we want to get another measurement of their energy and try to understand what type of particles they are. So then we put tons of material, literally gazillions of tons of material in their pathway. So we have, in CMS, we have these crystals, and they will stop electrons or photons. And you see that. In these layers, electrons, photons are being stopped. Particles with quarks will pass through those layers, actually, and they'll go into layers that are designed to stop them that have this brass that I showed you, for example. Then, so depending on where the energy is deposited, we get an idea of what type of particle it is. From the curvature, we know its charge, we know its momentum. And the things that go out completely, muons, are like heavy electrons. They get all the way out. And then we have on the outermost shells, we have muon detectors. Neutrinos also get out, but we can't detect them. Although a neutrino physicist pointed out to me that in coming years, we will actually have maybe 200 or so observable neutrino interactions in our end caps in the future. But that's out of, like, you know, 10 to the 18th. We'll never see them. So we don't see neutrinos. We detect them in some sense by an absence of balance. You have lots of energy going out sideways this way and nothing this way. Something had to be there to balance it, because when the beams are coming in, there's no net momentum perpendicular, so it has to be conserved, right? So if something comes out this way, something should have gone that way. So that could be neutrinos, or it could be dark matter, or any other kind of really, some other types of really interesting things. Okay, sorry, I spent a lot of time on that. So there's about 2,000 bunches in the beams. They're about this short, and then they cross every 25 billionths of a second inside the experiment. Each bunch has 100 billion protons or so. Protons are so tiny that even though the beam is squeezed down to about 1/4 of the diameter of a human hair, and that they're targeted perfectly, literally head on, you only get about 20 pairs of protons interacting each time. So we can keep these beams circulating and circulating and circulating, and you don't lose much. You know what I mean? And you just keep doing that until it gets a little weak. This is an actual interaction. You see all these tracks. They have a lot of curvature, which means they're low energy particles, not interesting. And then there's some interesting ones that get all the way out and deposit energy in the muon detector. So this is actually a Higgs candidate event for Higgs decaying to two Z particles, both decaying to muons, pairs of muons. So you can think of these experiments, if you like, as really ultra-fast digital cameras. They can run at 40 million pictures per second, if you like. They have very fast response. As I said, we have like 80 million channels used for the tracking of the particles, and the interesting events are actually really rare. So out of the 30 million or 40 million or whatever we have per second, we only keep about 1,000, 500 to 1,000. So we're throwing away by far the vast majority of the data. And that's partly because it's so much data. But it is kind of boring, most of it. Okay, so one of the challenges we have is that as we make the beams more and more intense, actually there are more and more pairs of protons that collide. And it's, at best you'll have one pair that's interesting. So all the rest is kind of just producing lots of noise, if you like, or debris in the detector. We call that pileup. So this is the case where you had two pairs of protons interacting that are not interesting. And you can see sort of the looking side on what the kind of debris is like, what that looks like. The same event, you know, with 5 or 10 pileup uninteresting collisions looks like this. And then by 2012 we had 20 or 30. And you see there's a lot of activity, and this is not relevant. I mean, we have to deal with that. So that was an interesting part of everything we had to do. This is a real event. Every one of these colors corresponds to a different proton-proton interaction. And this is, you know, this is looking at about a centimeter of the beamline. So you have a lot of activity. That led to really big data sets. So we set up a grid of computing worldwide. We have something like 22 petabytes of data in 2011, 30 petabytes in 2012. We expect to go up to, of order, 20 exabytes of data in the next 15 years or so. So we have a grid of about 400,000 computers in 50 countries. And you can see this is CERN, and it's shipping data out all over. This is actually a real snapshot of data transfers. And this shows you how big our data set was. We're bigger than the NASDAQ. Oops. We're not as big as Google, but not too small, right? Certainly not as big as Facebook. About as big as YouTube that year. Can you believe all the emails business people send? I mean, why is the economy such a mess? Because they're all sitting there sending. I'm kidding. I have no idea why. But I said we're going to have 1,000 times higher data set at some point. So let me tell you about the first big discovery, which is the Higgs. There are many ways the Higgs particle can decay. It decays almost instantaneously. We don't collect Higgs particles and look at them in a bottle or something. They decay, and we detect them by their decay signatures. Okay. So these are like the 5 main channels, but the 2 that I will talk about and that are really kind of key to discovery were these 2. The Higgs can decay to 2 Z particles. The Z's can each decay to 2 leptons. Leptons could be electrons, muons, or taus. And we're really in good shape to find electrons and muons, and not too bad at finding taus. 2 photons. Those crystals in CMS and the liquid argon system in Atlas are designed, and hundreds of millions were spent on them to be able to detect photons really well. So these are really good channels for us in terms of detector capability, but all the information is also contained in the final state, so we can recreate the initial state. And we can look for the mass of the particle that decayed to these things. We can calculate that in a very simple way. You have large backgrounds falling, but if there's a real signal at a fixed mass, you'll see a bump, because it'll keep decaying at that mass. So that's what we look for, are peaks in a mass spectrum. This is a CMS 2 photon event. There are 2 big towers here corresponding to lots of energy in the electromagnetic energy measuring device, the electromagnetic calorimeter. And this dashed line is just telling you that there was no track found pointing to them. So that means it has to be photons. Photons are neutral, they won't make tracks. And we collected lots of events like this, and this is the background distribution. You can have pairs of photons being produced kind of by much more mundane processes than a particle decaying. But if there's a particle decaying, you'd expect a bump. And that's what we saw, this little tiny bump. So what's in this bump? You have a few hundred extra events with 2 photons that reconstruct to a mass near 125 GeV, which is about 133 times the proton mass. How many collisions did it take to find this? 10 to the 15th. That's how rare this thing is that we're looking for. That's part of the reason it took so long to get there. Now, the really crucial thing is, of course, Atlas saw exactly the same thing as CMS in the same place. So even though it wasn't a huge bump, it was significant, and it appeared in both experiments. Here is an event in which we have 4 leptons, a pair of muons and a pair of electrons. And this is a candidate for Higgs decaying to 2 Zs, each decaying to leptons. Atlas has this is a very beautiful event from Atlas as well, where both of the Zs decay to electrons. And you can see the legs from those. And this is what you find. And was shown on 4th of July, I think. Yes. So this red distribution, okay, is what you'd expect for if you tried to reconstruct a mass from 4 leptons, just from processes we know in the standard model. Okay, you get this funny structure, but if you had a Higgs, particularly if you had a Higgs, for instance, at 125, like we saw in these other plots, you'd expect a peak here that matches this light blue thing. And you see the data actually is there, right? If the Higgs were heavier, it could be, you would have expected a peak here, but you don't see any data sitting on this. Or for even heavier, you'd expect it here, this green bump. You don't see any data sitting on it, but you do see it here. And CMS saw the same thing. And here I zoom in a bit, and you can see much better that this excess was there. So again, both experiments saw an excess in another channel that was just about what we'd expect.
Excuse me.
Yeah.
What was the rationale for choosing 2 dissimilar detectors? They could have had 2 Atlas or 2 CMS.
Yes.
Did they?
Because we can make mistakes for one. Well, it's actually comes down to the fact that I can answer this many ways. First of all, why do we have 2 experiments? The question is, why do we have 2 dissimilar experiments? But let me say why we have two experiments to begin with. You need one to corroborate the other. You also double your data because the collisions are independent. And the experiments are not the major expense. They're expensive, but mainly the accelerator is expensive. The other thing is you have expertise in the field. And it's very distinct, and people have ideas of what they want to do. So when the collaborations form, they decide independently, based on their expertise, how they're going to do things, what's the best thing to do. And so there's a slightly random process in what's chosen. So some things are exactly the same. CMS and Atlas both have silicon pixel detectors at the center, followed by silicon strip detectors, for example, and then things start getting very different. There's a real advantage to doing some things differently because everything we do is the first time it's ever been done at some level. And there have been cases where experiments have failed. And so if you bet all your money on one technology and it turns out not to work, your whole program's gone. So it's nice to have some dissimilar technologies. And then finally, you have different systematic uncertainties to some extent. You would like to have different ways of looking at the same things, so you're not totally correlated. But those are many, and there are probably other reasons. But does that answer your question at all?
Yeah.
Yeah.
Because when they discovered gravitational waves, they had 2 identical detectors.
Yeah, that's true. But the gravitational waves have never been seen before, for one thing. We've been seeing particles for hundreds of years. Oh, not hundreds, but over 100 years. Feels like hundreds, but. So it's. I think the reasons I gave you are the main ones. It depends on the expertise in the collaboration and what the collaboration wants to do. We do watch each other. We feed off each other a little bit. Atlas is always chasing us because we're always out in front. No, I'm kidding. That's what they say too. So we announced it on July 4th. It was actually simulcast to the biggest conference in our field, which happens every 2 years, called ICHEP. This is in the CERN auditorium. This is at Melbourne, where they were watching it. I like to show this because, physicists are not even into sports, but these guys are like, yeah, they got gray hair, gray beards hanging out. Yeah. So it was kind of fun. It was a big, exciting thing because it took a long time. Here I show the data coming in on the 2 experiments, 2 different channels. I show a new one, for instance, Higgs to WW. And you can see, if you look at the dates here, months are going by. And don't forget, we're getting 40 million collisions per second. So it takes a long time to accumulate. What was cute here, we didn't look at the data this way, of course, only afterwards. And you can see the red bump is showing what you should see if there's a Higgs there. And you see the data just keeps bouncing up to match it. It's kind of cute. And this, you see the same thing here. This red filling in there is what you'd expect if there was a Higgs. And so it has to be there. Okay. The other thing that's really interesting is if you look at, you can extract from all our data how strongly the Higgs must be coupling to the particles. Somewhat, because we know that the more the Higgs couples to the particle, the more massive the particle should be. So one indicator that you have a Higgs is that you measure the coupling strength. Versus mass should be a line, right? And that's basically what we see. There's a lot of detail in this that I'm not going to go into, but this is kind of a nice way, simple way of showing you've really got something that meets your expectations for a Higgs. The heavier the particle, the stronger the connection on the left. So this was later. This was after the discovery. This was about almost a year later. We had more data, lots more data. We had analyzed things. We felt much more confident that it was a Higgs boson. I went in. I was the guinea pig. I had to make a statement in a press release saying, yes, it's the Higgs, because we were worried that the press was going to start pressing us for some kind of 5 standard deviation statement that we didn't want to make. So I came out saying this is a Higgs boson. So then this was the news release. New results indicate that the new particle is a Higgs boson. It was actually exactly the same day something else was happening. I don't know if you remember, the Pope was selected that day. It was March 13th, 2013. And then we saw this. Okay, so how different are the two processes? I think we're a little bit more scientific, but it was very exciting. This led to the Nobel Prizes that year, as you know, Peter Higgs and Francois Englert. And we were very happy that they cited us. It really made it possible. So it was a really long time. This is the announcement of the Nobel Prize. Okay, looking to the future, we know there must be new physics. We know the standard model cannot be the whole story. There's too many things it can't explain. It simply cannot explain, and you'll hear more about this in a minute. There could be something called supersymmetry. So what is supersymmetry? It's a symmetry, and what it does is it takes all those standard model particles that I showed you, and you could say it just reflects them with a mirror, but the mirror is slightly distorted. So you get all these new images, these new particles. Everything's more or less the same except for 2 things. One is the spin. So if it was a standard model fermion, which means spin half, say, it becomes a supersymmetric partner that's a boson, spin 0. Spin 1 particles become spin half particles. So you basically find for every standard model fermion a boson partner, and for every standard model boson a fermionic partner. Did I just say it twice? You know what I mean. The other thing we know that's slightly different is that the mass of the partners is probably higher than the standard model particles themselves. There's a slight difference in mass, otherwise we would have probably seen them already. Some of the benefits of supersymmetry. For one thing, it unifies the strengths of all forces at high energy. Without supersymmetry, as you go to higher and higher energy, actually the coupling strength changes. I don't know if you know this. My students are always surprised to find out that alpha, electromagnetic coupling of 1 over 137, when we're colliding particles and creating Z's, it's 1 over 128. So you go to higher scales, it is actually diminishing. So they actually converged almost to the same place at very, very high energy, what we call the grand unified scales. But with supersymmetry, they really nail it to a point. And many people think this can't be coincidental. I once asked a really bright physicist, Ed Witten, if he believed in supersymmetry, and he said, yes. And I said, why? And he said, because of this. It predicts that there's a Higgs boson with a mass less than 130, and we found one at 125. So that's kind of interesting. And it provides clues to the dark side of the universe. So I'll talk about that briefly, and as I said, the others will tell you more. So here's the light side of the universe, right? Well, it turns out that, and you can kind of understand this, that as you move away from the core of the galaxy, there's less and less gravitational pull on stars. And so as the galaxies are spinning, the ones further out will be rotating slower and slower than the ones inner, and you'd expect kind of a dropping off of their velocities. right? Does it make sense to you? So the further away you are, less gravitational pull. You'd expect the velocities to fall. So you'd expect, as you get away from the curve, that the velocities of stars would be falling. Vera Rubin actually studied thousands of galaxies. You can look at the red and blue shifts in the plane of the galaxy and get the velocities as you move away from the core. And what she found was that instead of dropping off, they actually rise, okay? And if you think about a solid, if you had a solid sphere, right, as you moved out in radius, the segments of that sphere would be moving faster because they're all moving at the same rotational frequency, but you have a larger radius. So it's like there's something out there filling the galaxy, pulling these stars around gravitationally. And that's been known since the 30s. A very cranky Swiss physicist named Zwicky discovered it, but he was so cranky nobody wants to refer to him. No, I'm kidding. I heard he was quite a guy. I don't know. Maybe Lars, you know more about him. No?
I know more about him, but never met him.
No, I never met him. He saw it first. He called it dark matter. And so the name stuck. Vera really nailed it, I think, in terms of statistics and detail. So I have to tell you about the dark side. There is a dark side, okay? So what we now know is that only 5% of the universe is ordinary matter. 28% is dark matter, so there's a lot more dark matter than ordinary matter. We don't know what it is. The rest, I should say, SUSY, supersymmetry, actually has very good candidates for what dark matter could be, the type of particle it could be, and it turns out that if you calculate its abundance now, it's about right. So that's kind of interesting, and that's one of the things we look at. The remaining 67% of the universe's energy is called dark energy. I don't think we know what this is at all yet. It'll probably be taxed someday. I like to say maybe there'll be a Department of Dark Energy. Or maybe not, actually, because I've told you about supersymmetry just to show you that we know there has to be something beyond. Supersymmetry is one of the favorites. That's why we talk about it. But there are many other things. The absence of any supersymmetry data whatsoever has led us to think, or theorists to think, about alternatives. And these are typically characterized by new particles that do kind of the same necessary work that the supersymmetry particles do in kind of stabilizing the standard model, if you like. Or you can have more spatial dimensions. And recently I found out there's even theories with less spatial dimensions. As you get to very small scales, it could be that we lose dimensions. And there are many, these are some of the names of these theories. But the main point is if you don't know exactly what, for an experimentalist, the main point is if you don't know what you're looking for, having a machine like a Large Hadron Collider is just perfect. So we've done gazillions of searches. We haven't found anything quite yet, but we're starting to see some interesting things. We have literally probably 1,000 papers on searches from the two experiments. And now we're at much higher energy, so it's very exciting. So we're entering into kind of new territory. And there are some hints of things there, so it's going to be interesting. Last thing I wanted to tell you, do I have any time? 5 minutes or something?
Yeah, you have that.
Wow. I'm ahead of schedule. All right. I only have a handful of slides left. I just wanted to tell you about particle physics kind of in a different aspect of particle physics, what's it good for? And besides this, obviously, to us, it's extremely important to answer these questions. And we think that for humanity, it's very important to understand where we are in the universe. But there's no direct application of this information. So we're often challenged as why should taxpayers pay for this? But I wanted to point out that there are many other aspects to what we do, and convince you that even beyond this kind of cultural mission and scientific mission, there are some interesting and useful things coming out. First of all, you can see these are the different countries that are involved in CERN. There's about 60 countries. So CERN is really global. Particle physics is extremely global. People think it is not a U.S. program, but the U.S. is actually by far the biggest single country involved. So we have 17% of all people at CERN, or 15%, I say. There are actually 100 universities and laboratories in the U.S. alone that are participating. So there are 10,000 physicists worldwide. I think CERN staff includes only a few hundred physicists. So almost all the physicists come in and use this facility. It's a global facility. And it's great because you find that we all get along. So we have Iran and Israel, for instance, at CERN. And I can tell you some interesting stories about how they actually worked together to help each other do things. We have a Department of Energy partially built forward calorimeter in CMS that is on this really big set of jacks that could stay in hundreds of tons. And the jacks were built by Iran. So when the DOE visits, I say, here the US is supported by Iran. And it's kind of cool. We have Taiwan and China. You know, we have Pakistan and India. It's great. And we all get along, except for during, what do you call it? The World Cup. What is the soccer thing? Otherwise, we get along great. But is it useful? Okay. Here's an example. The coordination of so much technical information across the globe for CERN required thinking outside the box, which led to something useful. And that was this proposal by Tim Berners-Lee from the CERN Data Division, March 1989. He says here, this is a proposal that concerns the management of general information about accelerators and experiments at CERN. And that was a slight understatement, because this was the invention of the World Wide Web, actually. This is the proposal for the World Wide Web. I thought it was great. His boss wrote, vague but exciting. I bet he really wishes he could rewrite that now. In addition, there are accelerators for medicine, material studies. Superconducting wire was invented by our field to lower our power bill. So Fermilab invented how to make superconducting wire, and then spun it off to a company that immediately cornered the global market on niobium, I think. The World Wide Web I mentioned already. The grid, technology for the grid, doing this computing. Our students can submit a job, probably from their iPhone, on airport Wi-Fi. I don't know, I may be exaggerating a little bit, but I think it's almost that easy. And the job will run and find the data wherever it is, could be anywhere in the world, and return the answer to them. They don't have to know that. So we set up this massive grid of hundreds of centers, all interconnected, and that many people are looking to for other processes. So our computing experts that we train last about 2 years before somebody offers them $300,000 a year, and we have to train somebody new. But I think now we're sort of behind technology. Often we're leading because we have to do things no one has done, like the World Wide Web. But then, there are many ways in which industry then passes us, and we're quite happy to buy things rather than invent them ourselves if we can. I don't think we're necessarily leading in anything at the moment, except perhaps radiation tolerant devices. So just to give you an idea, as an example, we're preparing to replace part of the calorimeters in 10 years from now. They'll see a lot more interactions, a lot more radiation, very high data rates. So we're developing electronics here at UCSB with the engineering department that has to push data at the rate of about 10 billion bits per second, which is not so crazy. Things can already do that, but it has to sustain the radiation equivalent of 1 million Hiroshima bombs. And that is not done typically. So we have to do things like this. Okay, you can combine physics, biology, medicine to fight cancer. There are actually 30,000 accelerators worldwide. You may not know this, and 17,000 are used for medicine. You can target inoperable tumors, for example. And then we also do radiation detection. We detect particles. This has been used in much of our technology then goes into imaging, medical imaging, for example. But there are other examples. So anyway, in summary, we found this new boson. It was 40 years after the idea was hatched. It was 20 years to design and build the experiments. It took 3 years to acquire the data, as I showed you. It was really a generation of work by thousands. And all they got was this T-shirt, but But it was a giant leap, really, for science, and breakthrough of the year in 2012. Lastly, you can ask what's happening after the LHC. I'll show you very quickly. One thing that's being thought about in CERN is this is the LHC. They're thinking about another tunnel. This is Switzerland, by the way. So they're thinking about a much bigger tunnel, 80 kilometers around, or if that's not big enough, they're thinking about 100 kilometers. And so we'll start building it. I hope they start building this piece, because then if they cancel it, we'll at least have a fast way into Geneva. No, I'm joking. Also in China is considering it. I showed this slide in Peking, actually. I called it the Great Ring of China. That's actually to scale. This is the Great Wall. So we're thinking about the next step to go to higher energy scales. Obviously, it'll cost a little bit more. All right, so that's it. Thank you.
That was really great, Joe. Thanks a lot.
Plenty of time for questions. Let's do one over here. So in the planning and
So in the planning and development of CMS and Atlas, how much collaboration was done? Was that a dangerous thing, and that
Between the
ideas
two
might,
experiments?
between the two, and that ideas would converge, or
There was a lot of collaboration, I would say, in areas where we were using similar technologies or had to use basically, because we have to solve basically the same problem. I didn't say this, but the two experiments, perform almost identically well. Okay, they're slightly better. Atlas is slightly better at some things. We're slightly better at other things, but it's in the margins. We can all, Tom, you agree, right? We basically can do the same physics, which is great, but we use different technologies. But where we use the same technologies, we definitely, everything we do is public, first of all. So we're always reporting what we're doing, also in detector design. We have many detector conferences. And we report these things, and then we talk to each other, and we say, how the hell did you get that? And we don't believe you. And then they say the same thing to us, and we go back and look at things. So it's still aggressively challenging and understanding what we're doing. And there are a few places where I think we actually disagree about things still. But it doesn't matter. I mean, they obviously work. Does that answer your question? So a lot of things we do collaborate on. On the other hand, for instance, we have crystal we use for our electromagnetic calorimeter. Atlas uses liquid. So we don't even really pay attention much to that from Atlas. Not many people do anyway. Of course, we're interested and happy to see what they're doing, but we're not following that technology. Okay, so it depends on the technology. Data acquisition, fast readout, architecture design, we pay attention to each other a lot. And we gamble different ways, and then if one guy does better than the other, then the next generation here will follow them a little bit. So we watch each other a lot.
So is there a reason for it being underground? I mean, why couldn't you just build it on the surface and shield it somehow? Or
no, we need it. Actually, it's because there's a stable limestone shelf. The accelerator is amazing. Okay, remember this is it is probably the biggest machine ever built. It's 17 miles around. Okay, and you have particles going around at very close to the speed of light that then have to, before they right at the entrance to the experimental halls, they have to be focused, fired at each other, hit head on. And to give you an idea how precise that is, I heard an interesting analogy from one of the accelerator current leader of the LHC. He was giving a tour to some people that I was on because I was going to give a tour of the experiment. And he said, if you switch the protons for crochet needles, you know what crochet needles are? They're about that big. Then what they're doing is equivalent to firing crochet needles from either side of the Atlantic, Europe and the US, and have them hit on head on centered over the Atlantic, halfway in between. So now you have this device that's the size of a city that has to deal with higher precision than even precision devices, right? Things have to be incredibly stable. So they wanted to get down to where there's this kind of uniform, I think it's limestone shelf. Okay, so it's not necessarily shielding. Fermilab, the experiments are much closer to the surface. And this site in China is great because you hit granite 1 meter below the surface. So they go down, and it's the easiest to tunnel granite because you just dynamite it, take the chunks out and sell them, and just keep going. So they will build something there for pretty cheap. You get some money out. There was another question.
The future of next generation of accelerators depend on the success at 13 TeV and higher, that's going to play a critical role, or they're going to build
I
anyway?
think everyone's heard the question, I think. So you can debate this many ways. From our viewpoint, if we don't see anything, we really need this new machines, because there's one way to look at it is what we're doing is incredibly hard, and the reason we can pull it off with as few as 10,000 physicists, if you think about it, sounds like a lot, but what we're doing is incredibly hard. It's because we have generations of expertise. And if they say, you're off, we don't want to do this now, within 20 years, we can't do it again. I mean, it may take several generations to build up the capabilities again. And if they don't do it while we have everyone in place, what's going to suddenly make them want to fund it when nobody's in place? So this hit me a few years ago. If we turn off, this could be it. So the data we're taking now, sometimes I feel like, is we have to really comb it, really understand it, publish everything we can, because it may end up, hopefully not, but may end up having to stand for maybe thousands of years as the only high energy data out there at this level of detail. So we feel very strongly, even if we don't find anything, before we stop, make one more step, right? Look, there could be huge things just right there, right? If we don't see it with one more step, I think the field would probably say, okay. We'd probably try to make a case for the next step, but I don't think we'd be as... On the other hand, if we don't see anything, I think it's harder for us to convince our funding agencies. So there's that issue. And so there's a lot of discussion going on, and we're going to have a 2-week session here at the KITP starting in a week, right? Where this is exactly what's going to be debated and discussed. We're bringing in the top experts from all over the world, basically, on the physics, some on the machines, on the detectors, for all the future possibilities. And we're trying to figure out what do we want, what do we really need, how do we make the case under these different scenarios. Okay, so I didn't answer your question very well, but that's, you understand, it's complicated. It's very complicated, yeah. People will say this is a waste of money. But it's not, because it's huge spin-offs. Yeah.
Maybe a little different kind of question. I spend a lot of time in class trying to get students to think about what mass is, different kinds of mass, gravitational mass, inertial mass. What kind of mass are we talking about with the Higgs? I almost heard you, I think I did hear you say, in my mind at least, mass was almost defined as how much slower than the speed of light something goes.
Well, there are many ways to, I think there are many ways to look at things. This is probably better answered by a theoretical physicist. I'll tell you how I think of it, okay? And even a nice analogy for the Higgs mechanism. So, E equals mc squared. So mass and energy are similar. A photon is pure energy, right? What's an electron? It's also energy, but it has mass. So the mass is just like, as Einstein says, a very concentrated form of energy, right? So the way I like to think of it is that the Higgs will basically shield particles and concentrate their energy in a local area of space by interacting with it. And that creates it by creating a concentrated region of energy. In some sense, you're creating a particle. You're creating something there. If you take, for instance, photons, we know they're massless, right? But if you put, also that, you may hopefully know that superconductors, right? Fields cannot penetrate superconductors, right? So what happens if you put an electromagnetic field, a photon, inside a superconductor? Inside, say, a hollow sphere of superconducting material. If you write down the equations, you find the photon has a mass. The photon becomes massive. You shielded its field. You've concentrated it in space. And the Higgs mechanism is very similar. In fact, it's very similar even in terms of the mathematics. Does it help at all? Okay. So it's concentrating energy.
I remember hearing someone say a few years ago that if only the superconducting supercollider could have continued, perhaps the Higgs boson would have been found earlier. I just wondered if you'd want to talk about that a little bit and what possibilities.
Well, I mean, the superconducting supercollider was the size of the big machines that I showed you at the end. So it would have been a fantastic machine. We would have found the Higgs probably with a little less difficulty. We wouldn't have had to go to such intense beams and things. because we could have gone to higher energies. I'm not sure actually how big an effect that was. The cross-section should go up. But we'd certainly be able to access more physics. It would have been a better machine, no doubt about it. It was the best machine. By far, it was the best designed. In Europe, they used a tunnel that was already existing. Tunnels are not cheap. So the big tunnels I showed you, there are 5 billion to build in Europe. It's $1 billion in China. But
I was wondering why they needed superfluid
helium
instead of just warmer liquid helium.
It turns out, let me see if I can answer this well. So it turns out that the magnets, to get to high enough energy, to get to high energy in a circular ring, the bending magnets have to also be very strong. And they have to be able to go from relatively low field to high field. And the way I like to give an analogy of how this works is, imagine a race car going around a track. The tracks are banked, right? So the cars don't slide off. If you bank them more, the cars can go faster, right? So we kind of control the banking. That's what these magnets do. So they wanted to go up to 8 Tesla, 8.3 Tesla or something like this. And to get to that high magnetic field, it turns out you're very close to critical. The superconductors are pushed very close. We're 1,000 times closer to critical than we've ever been in any accelerator before. And so the colder you make it, actually, you can push yourself away from the critical line. So they go down to 1.9. They go down, but the other thing you gain by going to superfluid is there's no thermal gradient, right? If you have a superfluid, there are no thermal gradients. That also helps stabilize the magnets. But obviously, it's tough, right?
Where is a majority of the funding coming from?
The majority of the funding for CERN comes from Europe, the European states, and interestingly, it comes from the state departments, if you like, because CERN actually has 2 missions. One is to do science, the other was to help rebuild a unified Europe after World War II. It was started after World War II. So the funding for the lab, which includes the accelerator, to a large extent, the majority of it comes through treaties, very old treaties. For the experiments and any marginal improvements to the CERN budget, we go through science ministers of basically 60 countries. And then they have a meeting of all of them. I've had to make presentations to them all. And can you imagine what a nightmare it is trying to get 60 different countries to approve your project? But they're very, very supportive in general. And it goes, if you have a good case, and you're not asking for too much, they'll support it.
You could explain the U.S.'s role in CERN.
Yeah, so the U.S., people often ask me, well, is U.S. a CERN member? We're not a member of CERN. And people say, why not, And actually, nobody really wants us to be, including us. And it's not as negative as it sounds. If the U.S. were to join CERN as a permanent member, the different members have to contribute to the CERN budget in relation to their GDP, their proportion of their GDP, up to a cap. So the U.S. would pay a certain amount each year. And that would be less than they're actually paying now, to some extent. Because what we're doing now is we're not paying CERN cash, but we're providing tons of technology, equipment, accelerator expertise that they need, and then tons of physicists doing the detectors and so forth. So what happens is and then in addition to that, of course, U.S. has had a particle physics program which has led the world for generations, and European scientists have come over here, and they haven't had to pay big fees to do that. So there's kind of an agreement between the 2 regions that you don't have to pay the entrance fee, but you should be a substantial contributor. So there's now an agreement where the U.S. is going to put about $600 or $700 million into CERN over the next, we're talking 12 years or something. No, more than that. Well, 10 years, something like that. And CERN is putting money actually into the U.S. But it's not like pure cash. It's expertise and equipment and things.
My students are inspired by heroic stories of cooperation and collegiality amid very difficult circumstances. And I was wondering if you could please share the story you told us. You said you know about the Israelis and the Iranians cooperating.
Oh, that one I don't think I can tell. I could tell you, but then I have to kill you. No, I mean, it was an amazing story. I'll tell you in private sometime. Yes, exactly. It's an amazing story. But there are other cases that are pretty spectacular. I could try to think of. I mean, the U.S. and Iran and Pakistan. It's pretty impressive. I was invited once to visit the factory building part of the Pakistanis were building part of our experiment. They invited me to the factory. This is really during the height of the war in Afghanistan, and the factory's right on the border. And I said, well, how will I know I'm safe? They said, no problem, we will protect you. I found out they were going to have a regiment of 400 soldiers. And guys with machine guns at the door. And my wife said, how do you trust the guys with the machine guns? I'm like, yeah. And then I stalled a couple years, and then Osama bin Laden was killed, remember? And then the Pakistanis said, we don't think you should come now. It's not safe. But I'll try to think of some. So there are lots of historic stories, and we get together incredibly well. We support each other very well. There's no real issues. I think the only time we start getting a little grouchy with each other is when we're looking at the data, because the data is exciting and there's a lot of competition. Who's going to get the result? Who's doing the analysis? Whose analysis should be the public one, you know? But like building these things is incredibly fun. And really, other than all of the reporting, going after the grants and reporting to the funding agencies has gotten to be really heavy. The first detector I built had 2 years. No one ever asked me anything until 6 weeks before installation. They asked me for a schedule. That was it. I showed one. I had a handwritten one-page schedule, and they said, "Okay, good." Next experiment I worked on, next project I did, I had a 350-line project file, and I had to report every quarter. Now we report every week, and it's like 100,000 line or whatever it is. But we're meeting with the DOE and NSF every week, and we have these major reviews, and it's getting really heavy. So that's not fun, but actual building and working with physicists is still very fun.
I don't know if you can help me answer this question. You said that now we know that there's something beyond the standard model. Do you know, or the story, or understand what happened when there was a time when we thought, when we find the Higgs boson, we'll have all the answers. And then we started to realize, even before we found it, that there were more questions.
Yeah. I think a lot of it was already known. I think the thing was that people were trying to see if we could finish this model of all the things we see in everyday life. Do we really understand everything we see in everyday life, sort of? And that was the standard model. And the Higgs boson does complete that, and it's really astounding, right? We now have this model made up of several different field theories that, in some cases we can do calculations there to 15 decimal places and do measurements that match all the way. It's amazing in quantum electrodynamics. In the strong fields, QCD, quantum chromodynamics, it's harder to do the calculations. They're actually getting very good at it. This Lance is one of the best. And we're finding that we're matching perfectly with the data. That we could do these calculations of these unbelievably complicated, strong processes, and they match to what we see. So we have this incredible description now of the fundamental world, but we don't understand anything. That's a fair thing to say, right? We have an amazing description. We can predict everything, but we don't understand it. Where did it come from? So then you have to ask, what's the underlying framework? That's what string theory is looking to try to understand. But the standard model has fundamental problems, okay? The Higgs boson, which has no spin, it's the first particle ever found with no spin. If you calculate quantum corrections to its mass, they explode. The mass should not be where it is as far as we can tell. Something stabilizing it at this level, when that kind of situation has arisen in the past, we found that there was an additional symmetry that usually created that stability. So supersymmetry is one possibility. There's also the possibility there's nothing else. Just standard model, maybe the dark matter is actually some standard model manifestation that we don't understand. Dark energy may be something that's very simple, I don't know. Cosmological constant, write it off as that. And it could be that our universe just happens to have these parameters, and there's no more to it. Nature just... And this is one of a gazillion universes. Just happen to have the parameters that allow life to exist. And of course, we're here. And then we can talk about it. But we're hoping that direction is not even relevant to me as an experimentalist, because I can't test that. So what we were going to try and do is find out if the universe is where it is because something's driven it there, a symmetry stabilized it there. And of course there is this dark matter. And it's not easy to explain by standard model. So we knew all this stuff before, but now it's the pressing problem. Right? The Higgs really exists. Okay? Oh, there's one or two back there.
Earlier you were talking about the magnetic field with liquid helium.
Yeah,
you mentioned
superfluid helium. Yeah.
And you mentioned it reaching critical. I've always wondered what you
what's
mean.
Reaching critical is the superconductors.
Yeah, what does that actually mean? I've always wondered that.
Superconductors.
I'm not of the physics. I'm
That's
not a
okay.
physicist.
No, I'll try to explain it. It's just that if you take a superconductor is an amazing thing, right? It's where you've stabilized the lattice of the ionic lattice of the system so well that the electrons start interacting with each other, and they form pairs, and the pairs are bosons, and bosons that like to jump into the same state. So you get superconducting response. You get perfect dielectric. Okay, but that state is actually very delicate. Okay, if you raise the temperature a little bit, it breaks down. The ions start to jiggle too much. Okay, if you have the field go too high, it breaks down. Okay. And it turns out that if you push the current too high, that's what drives the field high, it'll eventually break down. So that's what we call critical. What current can you push it to before it breaks down and is no longer superconducting? And yeah, that's the critical point I was talking about. It turns out if you make it colder, then you actually, for a fixed current, the colder it is, you're moving below this critical point. So you're giving yourself some breathing room. Okay? Yeah.
Maybe a last question over here.
Yeah.
Great
this
questions, by the way.
is probably very simplistic. One of your first slides were all these very, very straight lines and then intersecting, and then you mentioned that that's actually protons.
Oh yeah.
And I'm just wondering, how would protons in a magnetic field make these very straight lines?
I'll show you. Good point, if I can find it. Where the heck was it? I think it's here. Well, I have it here somewhere. Oh, here it is. Here. No, it's here. It's also in this one. It's the same picture. So the protons are colliding at the. You see all the particles are pulling. Like you see you see all these particles coming from a point. That's where the protons collided. What's coming out are not protons. Okay. So that's the debris or new particles that have been created, and they're really energetic. They're not all straight lines, actually. You can't tell because we've actually zoomed in on a region this big, so you don't see curvature yet. But a lot of them could be very low energy particles coming out. But it's a lot of debris.
Hey, that was really great.
All right.
Thank you again.
Thank you.
So before we break, I just wanted to make one announcement. We have this town hall session and then after Laura's talk, and I want all of you to think of sort of 3 different things I'm going to try to have discussions on. So I'm priming the pump before our break. So one is any values or any experience you want to share of the sort of challenge of hands-on learning now that kids actually aren't building anything. That's my perspective. So anything you have there that you want to share. Sort of challenges or, shall we say, advantages of information availability. And we're going to have a interesting demonstration of we're going to have a demo as well. from Melinda that we'll hand out on not quite information availability, but taking advantage of devices. So that's the second. And then if anybody has any experience they want to share on sort of the flipping of classrooms, which is commonly done now, I think, at least in the colleges and maybe in the high schools, either advantages or disadvantages or experiences they want to share. So that's sort of this random town hall session we have that will be after Laura's talk. So please think about things you'll want to do, because I'll try to get through all three of those and have you speak rather than me.
Lars, can I just say, what does it mean flipping a classroom? Can you define that for people who may not have heard of it?
So flipping a classroom is that you don't actually lecture, you rather tell the students to read in advance or do something in advance, and the classroom is much more interactive and in the university setting often a homework-based, or shall we say project-based within the classroom. So that's one version of flipping, but I'm more interested in hearing what others think about that. So we'll do that after Laura's talk, but before lunch. So please do think about those topics. And if you have anything else that you feel like we should do, talk to me at break. The break is in the courtyard, so just go directly out and in that direction.